Hello, today I'm going to be going over reinforcement learning. So, reinforcement learning is a really interesting area of AI. It can be really complicated sometimes. It took me a while to learn it, but when I understood it, it is so cool. Because it's not exactly just about predicting an answer. It's about learning through actions. Instead of being handed the correct label or answer, an agent has to interact with an environment, make its decisions, and then receive rewards or consequences based off of those decisions, and slowly improve its behavior over time like that. So you can think of it as like learning a game, training a robot, or figuring out a strategy. Actually, those are the most common uses of reinforcement learning, such as creating an AI chess bot. Yeah, the learner does something, the world responds based off of that action, and then the learner updates what it believes is a good decision. So, for this video, I'm mostly going to focus on the more visual and conceptual side of reinforcement learning. So, you don't exactly need to know the math to follow the main ideas. Like, we're just going to be talking about agents, environments, and yada, and Q learning and DQN and other major reinforcement learning methods in a way that is more intuitive. However, I do want to say that the math behind reinforcement learning is still really important. It's pretty good. To me, math is almost like a language. So, math, honestly, it translates all these lines of code, like algorithms, to just one simple sentence. It lets scientists and researchers express ideas very precisely, like how much the future should matter, how valuable a decision is, or how an agent should update after an experience. It is really helpful, and especially in this area of reinforcement learning. Now, before we dive straight into reinforcement learning, it would help to compare it with the types of learning people usually hear about first. In supervised learning, the model is trained with examples that already include answers. For example, an image might be labeled cat, dog, or car. The model tries to map the input to the correct output. The world does not change because the model guessed something. If the model misclassifies a picture, the picture does not suddenly transform into a different picture. The model is wrong, but the environment is not affected. In supervised learning, there is no definite answer key. The model tries to discover structure. It may group similar users, cluster similar images, compress data into like a smaller representation, but basically identify hidden patterns. Again, this this type of learning is mostly observational. The model is looking at data and trying to understand the sort of structure or organization behind it. Now, reinforcement learning is different because the learner acts. The agent makes a move, and that move changes the next situation. For example, a chess engine chooses a move, and now the board is different. A robot takes a step, and now its body position, balance, angle, all that stuff has been changed. A self driving car turns slightly, and now it's in a different lane position with different risks, different angle, etc. A agent is not just predicting a reality, it is participating in reality. This is why reinforcement learning is so interesting. The data set is not exactly fixed. The agent's behavior determines which experiences it collects. If it always repeats one exact behavior, it may never discover alternatives. It has to be able to take risks. If it explores randomly forever, though, it may never become skilled. So, Reinforcement learning is a learning problem, a control problem, and a strategy problem all at once. A simple way to say this is that supervised learning learns from answers, unsupervised learning learns from structure, and reinforcement learning learns from taking actions and the rewards it gets from taking those actions. All right, let's look at the main vocabulary of reinforcement learning. It's pretty small and easy to understand, I guess, but every word carries a lot of meaning. Like, it's pretty good to know. The first word is agent. The agent is basically the decision maker. It is the part of the system that chooses the actions. Let's look at a famous chess player. Honestly, I have to say I'm a fan of this dude. But he is the one that chooses his actions, how the chess pieces move. Like in a game, the agent might be the chess player, and robotics it might be like the robot controller. And yeah, it might be the agent is not the whole world though. It's just the learner inside the world. All right, now let's look at environment. The environment is everything the agent interacts with. It includes the rules, the consequences, obstacles, rewards, and sometimes other agents. Say in chess, the environment includes the board, the legal move rules, and the opponent. And yeah, it okay. Now let's look at state. The state is the information the agent uses to describe the current situation. Like this could be a chessboard position, and it is pretty important because the agent's decision is based on what it knows in the present, the state. All right, now an action is something that the agent can do. And say an action would be how it can move a chess or one of the chess pieces movements. And an action is the agent's way of pushing on the world. All right, now reward is the feedback signal. It tells the agent whether something is good or bad, what happens after action. The reward is pretty tricky. It's pretty tough to understand, but a small immediate reward might lead to a bad future. A small immediate penalty might lead to a better long-term outcome. So, reward is not the whole story by itself. It's a local signal that the agent uses to build a larger sense of value. It's when you look at it, it's going to be pretty hard to understand. Oh, and the math, it looks hard. But now on to the policy. It's the agent's behavior rule. It tells the agent what to do in each state or the probabilities to assign to different action. A policy can be basic, rigid, like always choose this move in this situation, or flexible, like choose this move most of the time, but choose sometimes try another move. It is kind of like chess strategy. You play multiple chess games over time, and then you learn from them, and sometimes get a better chess strategy. All right, an episode is one complete run of the experience. In a game, an episode might begin at the starting screen and end when the game is won or lost. And let's say an episode is basically the start position of the environment, and then at the end, the environment is who won. Or no, the episode is who won. All right, let's look at a small story before we really dive deep. It'll be good to know this because it'll basically get used. All right, now All right, the Markov idea is one of the most important abstract ideas in reinforcement learning. It says that if the current state is truly complete, then the future should depend on the current state and current action, not the entire history separately. This does not mean the past is unimportant. It means that the relevant past has been compressed into the present state. Think about a chessboard. You do not need to remember every move from the beginning of the game to know most of what's legal and what position you are in. The current board contains the most of the relevant information. The past has shaped the present, but you do not need to carry the entire past as a separate object. A good Markov state is like a summary that is sufficient for decision making. Like, if two situations have the same state description, then taking the same action should create the same kind of future possibilities. That's the ideal. It makes problem manageable because the agent can learn transitions between states instead of memorizing every possible history. When the Markov idea works, it turns a huge memory problem into a basic transition problem. Instead of asking, what should I do after this exact long history of that ever happened? The agent asks, given the current state, what actions should I take? That asks a much cleaner learning problem. But the weakness is important too. If the state hides relevant information, then the agent is not really in a full Markov world. For example, if the robot only sees one camera frame, it may not know whether an object is moving. If a game agent only sees the current scene but not previous scenes, it may not know velocity. If a medical decision system only sees today's measurement and not the trend, it may miss important context. When the information is hidden, the problem becomes partially observable. The agent may need memory, a sequence of observations, or a recurrent network to construct what the state should have included. So the Markov assumption is powerful, but is also an assumption. It is one of the places where a clean mathematical model may simplify a messy real world. It is amazing, trust me. Alright, whoops. I showed the wrong slide, but here is the. Alright, now into transitions. Man, transitions make things a bit harder. So, a transition is what happens when the agent takes. So, again, the state at a time, an action at a time, to a reward at a time, to now. Alright, so reward is the immediate feedback signal. It answers the question, what happened right after this action? Did this agent gain a point, lose health, or reach the goal? Waste time or hit an obstacle? The policy is the agent's behavior rule. It is not the environment, it is not the reward, it is not the value function. It is a rule the agent uses to choose directions or actions. A deterministic policy gives one chosen action for a state. If the agent is in this situation, it does this action. There's no randomness. This can be useful when the agent is confident and the environment is stable. A stochastic policy gives probabilities over actions. Instead of saying, always do this, it says, do this action more often, but sometimes do these other actions. This is useful for exploration for. Alright, now deterministic policy, which is same state, same action. A deterministic policy is the simplest type of behavior rule. For a given state, it selects one action. If the agent sees the same state again, it selects the same action again. The future or past actions don't really matter in this case. This is easy to visualize. The state is like an input node, and the policy points to one chosen action. Other actions may exist, but the deterministic policy does not exactly sample among them. It commits. This can be useful when the agent has already learned a good strategy. For example, if a maze agent knows best move from each location, it may not need randomness anymore. Now on to stochastic policy, behavior as a probability distribution. A stochastic policy does not choose one action. Alright, now on to Q values. This is really important to differentiate a state value and a Q value. A state value tells us how good a certain situation is overall. A Q value goes one step deeper. It asks, if I am in this state and I take this specific action, how good is that choice expected to be? This is extremely useful because decisions require comparing actions. If the agent only knows that a state is good or bad, it still needs to know what to do there. Q values attach value to state action pairs, so the agent can compare possible moves. Imagine standing at a intersection in a maze. The state is your current position. The actions are left, right, up, down. The Q value for go right may be high because it leads towards the goal. The Q value for go down may be low because it leads to a dead end. The agent can choose by comparing these action values. The deep meaning is that Q values act like a decision compass. They do not only say where you are, they say which choices from here seem promising. That's why Q learning and DQN becomes so important later. They are built around learning these action values. Once an agent has good Q values, it can often act well by choosing the action with the highest estimated value. Alright, so Bellman thinking. Now there's an equation for this. Exploration vs. exploration is not just a side issue in reinforcement learning. It is one of. Alright, now into the greedy policy. Yeah, the greedy policy, because it's greedy. Greedy policy chooses the action that currently looks best. It looks at the estimated action values and picks the largest one. Thus, it's greedy. This is pure exploitation. Epsilon greedy adds a small amount of exploration. Most of the time, the agent chooses the best known action, but some of the time it chooses randomly among. Alright, so now onto the softmax policy. I don't know. This excites me. It might excite you as well, because, come on. Some people might have heard of softmax before. Remember, in other areas, not just reinforcement learning, this is a probably popular area. I remember it. Now onto model-based vs. model-free reinforcement learning. Alright, so now onto dynamic programming. So Dynamic programming is a family of methods that work when the environment model is already known. That means the agent already knows the transition rules and rewards. It does not need to discover them by trial and error. The basic idea is to repeatedly update value estimates until they become consistent with the model. If you know what can happen from each state in action, you can sweep over the states and improve your estimates. So, policy evaluation asks, if we follow this fixed policy, how good is each state? It judges a behavior rule. Policy improvement asks, given these values, how can we choose better actions? It improves a behavior rule. Policy iteration alternates between those two processes. Evaluate the policy, improve the policy, then evaluate again. Value iteration combines evaluation and improvement more directly. Instead of fully evaluating one policy before improving, it repeatedly updates value towards better choices. Dynamic programming is elegant and foundational, but it assumes we already know the environment. In many reinforcement learning problems, we do not. The agent must learn from experience instead. That leads us to the Monte Carlo and temporal difference model. See, it is pretty annoying. Every little thing has its own problems. Alright, on to Monte Carlo reinforcement learning. So it learns from the complete episodes. Instead of updating immediately from a partial guess, it waits until an episode finishes. Then it looks back at actually what happened and uses the observed outcome to update value estimates. Then, okay, alright, now on to Q learning. So, Q learning is one of the classic reinforcement learning algorithms. Its goal is to learn how good each action is in each state. Once the agent has learned good action values, it can choose the action with the highest value and behave well. The important idea is that Q learning learns from experience one transition at a time. The agent is in a state, takes an action. SARSA is another temporal difference control algorithm. Its name comes from the sequence it uses: state, action, reward, next state, next action. So the key idea is that SARSA updates using the action the agent usually makes next. So this makes SARSA. Alright, here's a slide to look more at SARSA. Alright, so tabular reinforcement learning stores values in a table. For every state in action, the agent can keep a separate estimate. This is clean and understandable in a small grid worlds, but many real problems have this enormous or continuous state spaces. A video game screen may have thousands of pixels. A robot might have continuous joint angles, velocities, camera inputs, and sensor readings. Two states may almost never repeat exactly. If an agent needs a separate table entry for every possible state, learning becomes impossible. This is called the state space explosion. The number of possible situations become too large for different direct memorization. The agent needs generalization, and it needs to learn that similar states should have related values or actions. Alright, so this is a big one. So DQN stands for Deep Q Network. It combines the logic of Q learning with the representation power of a neural network. Instead of of using a table to store the value of every state action pair, DQN uses a neural network to estimate action values. So, in a simple grid world, a cube table is possible because the state might be just a coordinate. But in a Atari game or a robot vision task, the state could be an image. There are far too many possible images to store in a table. A neural network can take the image as input, process visual patterns, and output a value estimate for each possible action, such as a CNN. The TQN network usually outputs multiple action values at once. For example, if the agent can move left, right, or jump, or shoot, the network produces one estimated value for each action. The agent can then choose the action with the highest value, or use an exploration strategy like epsilon greedy during training. The training loops work because, like this conceptuality, the agent observes a state. The network estimates values for the available actions. The agent chooses an action, then the environment returns a reward, a next state. That transition is used or stored in memory. Later, the agent samples past transitions from a memory and trains the network to make its value predictions more consistent with the observed rewards and future um, possibilities. Remember how important values can be. So, this was a really helpful thing. So, this memory is called experience replay. It is one of the major stabilizing ideas in DQN. Without replay, the agent would train only in the most recent sequence of experiences, which are highly correlated. If the agent is walking through a hallway, many consecutive frames are almost the same. Training on only those can make learning unstable. Replay mixes older and newer experience, making training more like ordinary machine learning batches. Experience can replay and also improve data efficiency. A real interaction with the environment can be reused multiple times for training. That matters more because collecting experience can be expensive, especially in robotics or stimulation that take time. Another key idea is that the target network, DQN, is trying to train a network using targets that depend partially on the network's own future estimates. That can become unstable because the target keeps moving. To reduce this problem, DQN keeps a separate target network that changes more slowly. The online network learns frequently, while the target network is copied from the online network only occasionally. A good analogy is learning from a teacher whose answers do not change every second. If a teacher constantly changes while the student is learning, the student can chase a moving target. The target network makes learning more stable. So, DQN has three major ideas working together. Q learning tells what kind of action values to learn. The neural network lets it handle complex states like images, and stabilizers like experience replay, and target networks make training less chaotic. DQN was important historically because it showed that deep neural networks could learn control policies from high dimensional inputs, like raw game scenes using reinforcement learning. It helps launch the modern deep reinforcement learning era. But of course, DQN also has its limitations. It's usually designed for discrete action spaces like presenting or pressing buttons. It can also be sample inefficient. It can be sensitive to hyperparameterization. It can overestimate action values, and Because it learns through trial and error, it can require huge amounts of interaction. Later methods improve on these weaknesses in different ways. All right, now this is another slide too, also. And this is also another slide because. All right, so Q learning methods learn action values and then choose actions based on those values. Policy gradient methods, gradients, math. Anyway, take a different route. Instead of first learning how good every action is, they directly adjust the policy to make successful actions more likely. See, optimization, gradients, okay. Anyway, think of policy as a behavior generator. It looks at the state and produces action probabilities. After the agent experiences outcomes, the algorithm adjusts policy. Actions that help produce good outcomes become more likely in similar situations. Actions that led to poor outcomes become less likely. This is especially useful when the action space is continuous. A robot arm may not choose from only left or right. It may need to choose exact monitor torics or continuous movement or other nerdy robotics. Anyway, so Q learning over discrete actions may not fit naturally. Policy gradient methods directly output continuous actions or distributions over continuous actions. See, math is seriously useful. And policy gradients are also useful when we use stochastic policies. In environments, the best behavior might not be fully deterministic, or the agent may need controlled randomness. A policy gradient method can naturally learn probabilities. The downside is that policy gradient learning can be noisy, and the agent may need experiences to know which actions truly cause success. If the episode goes well, many actions happen along the way. Which actions deserve credit? This is also caused the credit assignment problem. It is one of the hardest problems in reinforcement learning. To reduce noise, many methods use a critic or a baseline to judge whether an outcome was better or worse than expected. That leads directly into the actor-critic methods. Now, you might really correlate this to other topics such as in supervised learning and neural networks, gradients when you learn optimization. You can also think about other issues that come with this, such as maybe having a local minimum or maximum, right? Because there could be a local one and there can be the most biggest one, and sometimes the gradient can choose the wrong one. It really connects to other topics. It's pretty good. All right, so now to the last thing, the reinforcement method map. So at this point, reinforcement should look less like a list of disconnected algorithms and more like a map of ideas. So if the environment model is known, dynamic process or programming can update values by sweeping through states. If the model is unknown but we can observe full episodes, Monte Carlo methods can learn from complicated results, or completed ones too. So if we want to learn during an episode, temporal difference learning updates from partial experience. Now, thank you for listening. I hope I truly helped you guys. And thank you.